Hello, my name is Michael. You're welcome to my YouTube channel. Today I'll be talking about the part 3 of this topic, which is IPv4 IPv6 network connectivity. Here is the agenda. So we start with a question which is referencing the previous videos. If this is the first time you are seeing my video, please note that this is part 3 of the topic. So if you want to see the previous topics that I've discussed, you can check in the description for the link to the previous videos, so you can get to understand why the question and how relevant it is with respect to the topic. This question is simply, what if there are no restrictions for both versions to coexist? After that, we will talk briefly about the dual stack solution itself, and I will show you the scenario I've prepared also for this video, after which we will do a little bit of some implementation and the verification of those, and we will then see the packet analysis, how these packets appear on wireshark. Then we can wrap it up from there. So let's dive in. Here, it's still looking at the previous state where you have separation between the infrastructure of IPv4 as well as IPv6. And that's simply because different scenarios can play out to bring this into reality, where you have IPv6 only as well as IPv4 only, and they have to interact. And that's actually been covered in the previous video. In modern network infrastructures, we have more powerful devices which are now designed to be able to hold the databases of both IPv4 as well as IPv6 operations. And this means you have devices now that are really powerful in terms of the hardware resources, and this includes the CPU, the memory, the disk storage, and the IOPS, that is the input-output buses as well. They are now designed to be able to hold on to large sizes of data as well as compute capacities. And that's really a good one. And this makes it easier to have both IPv4 and IPv6 coexist on a device, which you will find in most places today. That makes it really interesting for us to see the dual stack solution thrive in different scenarios or different projects, such as transitioning projects where you are moving from IPv4 to IPv6 and you want to have an interim solution that makes both of them coexist, and this is actually what will play out in that case. You also have it leading the front line, especially when you're doing migration of one system or solution to the other, and you want to host IPv6 as one of the transport protocols that you would need, or transported protocol rather, in that case. And in this case, you also could see this deployment in research and development environment, and this is really heavily used during merger and acquisition, especially when recently merged or acquired entity is going through the phase of unifying its infrastructure into probably a pre-existing one that has IPv6, and you want to extend this further. You need a solution that allows you to do that transitioning easily. Of course, you can see this also in POC scenarios where proof of concept is being driven in order to win deals, in order to convince your customers or partners basically regarding IPv6 concept. And of course, this is very important for any kind of business purpose that you might want to use it for. So in summary, IPv4, IPv6 are able to coexist in the same infrastructure, but they are also parallel at the same time, which means you can deploy all IPv4, all IPv6 on the same set of devices, and they have almost zero knowledge of each other. What makes this possible is that every device has something called the device plane, or in some cases you find it to be operations plane, or whatever name that you see in documentation. These planes are mostly the databases of different mechanisms that allow systems to work properly on the network. For instance, you have the control plane, you have the data plane, you have the management plane, you have the orchestration plane in the context or in the scenario where you have SDN or SD-WAN solution. You also have the security plane. All of these planes are simply databases of data which are responsible for certain operations on each device on the network. In the case of the control plane, you're simply talking about the routing protocols and any other protocol that is gathering information or intelligence of the network. And this can be central, it can also be distributed depending on what model you are looking at. There is also the data plane, which is responsible mainly for the forwarding of data across the network. You have the management plane, which allows you to administer the devices on the network. If you want to do any management accesses, this plane is responsible for that. Then the orchestration plane is mostly found in SDN, as I said before, as well as SD-WAN environment, and this is the part that is responsible for some validation as well as some onboarding of new edge devices or new controller into the fabric itself. SD-WAN, for instance, uses this so well. It's also the V-bond topic when you talk about Cisco or Viptela platform. Then for the security plane, you have a lot of devices that are operating in this scope that are responsible for enforcing policies as well as ensuring protection of the entire system. And these all planes can actually have databases that are strictly for IPv4, another separate database that are strictly for IPv6, which is why the solution itself is regarded as a solution that keeps the infrastructures parallel. That is, IPv4 has no knowledge of IPv6, but they are both there. And this makes it really resource intensive because you have to keep data for both versions. And if care is not taken in terms of the sizes of these entries or the sizes of the databases, it could affect the physical resources, that is the memory, the CPU, and this can actually lead to overall degradation. It's nothing different from faith sharing when you think about virtualization and faith sharing in this context. And that's exactly why it is important to plan very well before considering to deploy this particular solution. The planning of this solution is also easy to do because you have two parallel infrastructures that you can plan in isolation without having to worry about any interactions between them. However, it's also important to think about the impact of poor planning or no planning, especially in large area of deployment. Take for instance, if you have tens or hundreds of thousands of routes coming from IPv6 which are not summarized, and then you also have IPv4 which doesn't have that much, or perhaps it has even much more than that, you have to be able to foresee that when you inject those routes together, it will have a significant impact on the hardware resource on each of the components of the infrastructure, the router, the switches, and the likes. which is why it is important to ensure that the planning is done properly, even though it might appear to be easy. The same thing with the deployment makes it easier because in situations where you are doing transitioning, for instance, you are going from IPv4 to IPv6, but you just can't turn off IPv4 just like that. And that's why this usually serves as an interim solution to bring in IPv6 together with IPv4 and ensure that the network converges fully for IPv6 before gradually phasing out IPv4. And this is why it is considered to be one of the leading options during, IPv6 transitioning projects, basically. And of course, we find it interesting also because these two infrastructures are parallel. You could run one particular routing protocol in IPv4 and another routing protocol in IPv6, and you're totally fine with that. Doesn't have any problems. In this case, you can run ISIS or OSPF in either of those environments. But it's important also, the environment in terms of the scope and size also matter because of the kind of resources that it might require in order to hold both databases or both environments stable and reliable as well. So as you go into large environments, you tend to plan further to ensure that you don't blow up the resources that you have, because this solution can be very resource intensive in large scale deployment. Again, the support for dual stack scenario is very wide because a lot of protocols support it. Static route, default route, they both support it. Control plane protocols that we have here, they all support IPv4, IPv6 to coexist. The data plane protocol also, they support this solution as well. So it's very important to see that you can deploy them without the worry of compatibilities at all. So most important thing here is to plan and ensure that you select the appropriate protocols that you need to use. And here's the scenario that we have for today. Here is where I'm sitting. This is my home network, and this is my laptop, the one I'm using for this recording. I have a MikroTik router, which is actually dual stack. My system also is dual stack. Every system that you see here, they are dual stacked. So there is no problem about reachability at all. And most of them have been pre-configured. I only left one in order to demonstrate what we would do in terms of the implementation. And that's this router 5 here. But the agenda here is to show you that from my PC, I'm able to reach this server on both IPv4 as well as IPv6 addresses of this server. And that's where the end-to-end convergence comes in. At the moment, this is the only link that is left to connect, and the purpose of this video is to configure this interface as well as this interface to make these areas come back to life as it is, so that we can test and also inspect how the traffic is flowing. So the implementation plan is to start with the design, ensure that you have a good IP scheme for both IPv4 and IPv6. Then we configure the parameters that we need to configure in order to have the convergence, and that talks about individual interface with its own IP address for IPv4 and IPv6. We would also check in terms of the routing tables, see how the routing tables are able to hold the data, and compare things generally before we then check on the capturing part of the wireshark that we'll see for analysis purpose. So let's go into the next phase, which is the implementation. But first, I will show you my PC to see that we have a dual stack PC here, and that's where we have my IP address, which is the IPv6, but it is unique local. Remember, there are different types of IPv6 addresses, and here is the link local address, which is mainly for directly connected segments and not to be used for routing. It doesn't flow with that, even though it's considered as a peer IP in routing protocols, in terms of when you establish the peer between routing protocols. And this is the IPv4 that we have on it. And so if I would check to my gateway on this side, it's reachable, and if I would check to my gateway as well on IPv6, it's also reachable. So this is fine. Now we'll take you to my Protic router, which is actually here, and that's the gateway that I have for my home network. As you can see, I have BGP configured, and here is the IP address that I was trying to reach, or which I reached before, 97.1. The same thing applies for IPv6, which I was able to reach the unique local, which is here, .1 as well, or colon 1. If we quickly take a look at the route table or routing table, you would see there are a couple of routes. You can ignore the static ones, but the BGP route for my lab is here. As you can see, it's the lab path that we are learning these addresses from. These are the routers that we saw before. These are also the routes that are coming from my lab environment. Quickly, I will show you the BGP config, which is actually here. So I have an instance of BGP called MyCloud Wireless LAN, and here I have the basic configuration and the redistributions from the connected as well as static, so that the lab can learn some of these things that are configured. For this, we can see also here that we have my lab, which is running IPv4 as well as IPv6. This is the same device, and that's where the multi-protocol BGP topic comes in. When you see here on the advertisement, we can see the addresses that are being advertised to the lab environment, and you can see all of these addresses are being advertised, as well as the IPv6 prefixes as well. Now we go to the VLab router. So I'll quickly open my secure terminal. So, and here, if we quickly check that we have access, we can see that this is the IP address that we saw before on the Protic side, and the same thing applies in terms of the IPv6. So this is also dual stack, and if we check the BGP table, you can see that we are learning 22 routes from it, and it's actually on the Protic side. Further, for IPv6, you can see these are the two routes, and we can also check that from the receive routes perspective. You can see we have both of them being received, even though one is actually recursive, which is RIP failure because it already has it in its table. So if you would also check the OSPF table and neighbor table, it shows that we have only one peer or one neighbor. If we would go back to this, it's meant to have two, but like I told you before, this was actually shut down and we have to configure that interface. So currently we are going through here, and the same thing applies when we go to router 3. If I have to check that, you would see I have this, or perhaps we go to router 2. Yeah, router 2 should ideally have two neighbors neighbors, but it has one, so only this path seems to be okay. That's for IPv4. And to check that this is alive, we can also see that router 2 is able to reach the server. The same thing in terms of the IPv6 to 4. So you can see the server is alive in terms of being dual stack. And now we do IPv6 also to check neighbor adjacency. You can see it's only, just this side. And we can go now to the VLab to check. You can see also that it's only seeing this path alive, but not this one. And if we go on to, let's say, router 3, we check, you can see it has, the connection for most of the other things within its own path, which is good. And if we want to check the database, you can see that we are learning different IPv6, prefixes from different angles, from 5, from 4, and 3 itself, as well as 1 is not seen there. Okay, this is 1, which is actually in the other area, and that looks good. So if we check again for IPv4, and then we check the database. Now we are talking about the control plane in this case, so you can see how many routes have been kept for each of the infrastructures, and you see that they are not linked in any way to each other, which tells you if we had 10,000 of this and we have another 10,000, that's 20,000 in a row, and that's also going to impact certain things in terms of the memory and the CPU for lookup purposes. So now that we have seen the basic things, by the way, this is the MikroTik as well, which is VGP peer print. You can see this is actually lab instance, and this also is established. If we do details, you can see it's just giving us more information there, showing what VGP configs that we have. That's basically just to check the status. And now we will go into router 5. I need to check what interface it is. So interface 1 and 2. I already created the config for those interfaces, so I'm just going to copy it, paste, so that we can save as much time as we can. Let's go back. So navigate ourselves up to this point. So we go for, okay, I think it's 0/1. All right, and now we check what we have prepared. So this is the first one. I have the IP address here, which is the same subnet as the other peer, and I have this to be in area 0, while this is in area 4 to 5. Like I told you before, they can be parallel, so you can have different kind of topology between both of them. In the case of IPv4, you can have a separate topology compared to what you'd have in IPv6, and they are not in any way interacting with each other. So I have to copy this one and then paste it here. And now we unshut that. The same thing, we go to the other one and then we paste it. Okay, so we shut this as well. Then the next is to check that we now have the established neighbor adjacency. If we go back here and then we call back this, you can see it now has the 5 as its own neighbor, and in the case of IPv4, you have it also here, which then means by the time we check the routing table for this one, we begin to see even more things. You can see this also shows that it's learning things through two different paths, and that's, you can see also that it's learning by the link local address between them. In both cases, that is actually fine. The same thing here. If we call this back, we now have the 5 being added to it. The same thing applies for IPv6, IPv4 in this case. So just take out the 6 away, then we check again. So you can see 5 is now alive as well. It's now telling us the network is fully converged now. Next thing is then to go back to my PC and then try to reach the server on its IPv4 address, which we have here 233, and that's basically what we're about to do. You can see here it shows that we have reachability in order to confirm that indeed it's going through the path that we want, which is 2.5. We can see the path is going through .5 as well, exactly. Let's now try the same thing for the IPv6, which is FC05 2026 50 and then 2. Sorry, that's my local address, so that will be 2026 1147 124 22. Let's just confirm that that is indeed correct. 114112. Okay, that's correct. Now we can try again. Yes, that's reachable. Trace route to see how it's flowing, and we can see that indeed it's going through 5 again. For us to be sure, we can actually run a wireshark. Now we are now looking at the next phase. The ping is done. We can also do the SSH in order to just confirm that we are fine. I will target 192.0.233. That's the server which is responding, and you can see it's actually the same one. When we check this out, you can see it's to our stack, and that's the same thing here, which looks good. If I take it out and I try also again with its IPv6 address, I have the same results, which simply means I'm fine with both IPv4 and IPv6, and that's actually how dual stack appears to work, and that's basically because the network is converged. Now in the case of packet capturing, I am currently here. I want to see what's going on when I do the capture. And now we just have to filter based on the addresses 233 or IP address equals IPv6 equals 2026:124:124:2. So what we are trying to do now is to check what actually happens when I try to reach the IPv6 address of the server. I can already see what's going on there. You can see that's the server, that's my IP, that's the server. If we go to check, let's just pick one of these, or perhaps we can maybe go to the top, which is the initialization point. You can see here it tells us what kind of addresses there are there, and here you can see it's a unique local unicast address, and it tells us a unique local address. Meanwhile, this is a global unicast address, which is another type, and this is the one that is similar to the internet routable addresses. And of course we can also see other instances of link local addresses basically. So this shows that we are fine up to that point. Then if we go back again and target it using the IPv4 address, you can also see a similar case, which is now telling us, oh, you're using the IPv4, and that's also very separate from what we have for IPv6. So this is how it is. Dual stack is very, very easy to work with. The only part that you need to worry about, which is one of the two cases that you need to worry about actually, is the fact that it's resource intensive. At the same time, it is coming also with a lot of configuration overhead. And what that simply means is you have to do different configuration for IPv4, IPv6 separately. And you can't actually replace that in any way. It's why when you have to consider this is part of the things that you need to think about. So I hope that this has been quite informative for you. The conclusion here is that dual stack is a good solution for whatever environment that you want to use it for, and in terms of the ability to be able to deploy this in any environment, this is actually possible to be deployed in enterprise environment, data center environment, internet service provider, carrier service provider, as well as managed service providers, depending on the environment. Even the cloud environment, you can actually deploy this on AWS, Azure, Google. They all support this solution. Again, resource intensive nature of this solution makes it important that you have to plan it very well, especially when your environment becomes large, because sometimes you're starting small and somewhere along the line you just realize, oh, you now have a very large environment. So you need to plan this for scalability purpose as well as the manageability aspect of it. The high configuration overhead is also a thing that you should worry about when you see that this environment is going to grow. So you should be able to plan your design and how you want to operate this dual stack environment. Maintenance is of course very important, but like I said before, you will be doing a little bit of duplications from different points of views. When you do things in IPv4 to maintain, you have to also maintain IPv6 as well. The transition of IPv6 is really good with this solution, because you can move from IPv4 to dual stack to IPv6 in that progression, and it makes life easier for you eventually in order to move from IPv4 to IPv6. And the support you get also from all routing protocols basically that will support dual stack as well as IPv6, IPv4 together. That makes it easier to consider this. The same thing with the data plane protocols, and of course you have a lot of network services or protocols or applications that support the dual stack solution, which means they are able to provide you access on the services in terms of the DNS, the DHCP, NTP, FTP, SMTP, even as well as SNMP as well in this case, and so many other kinds of applications that you can think about on the network that already supports dual stack, which makes it easier to consider this because the compatibility issues have reduced drastically. The only part that you need to then think about is on the user application side, because of course developers are doing things every time, but not all environments actually have this support for IPv6, and not all applications are designed to support IPv6, which is why you will always find out that at some point you will run into having to translate between the versions, and in some cases you have to tunnel through certain areas in order to bypass some limitations that may exist on the network, and so many other scenarios like that. And importantly, it is very, very critical that you have to plan in order to ensure that you get the requirements ready to be delivered and met. And in that case, you have to plan the infrastructure before you start your implementation. I hope that this video has been helpful. Please take your time, go through it. If you have questions, you can write me. I'll be happy to respond to you. And don't forget to like and share. Also subscribe. You can just click on the bell notification in order to get alerts when I release another video. Thank you, and I look forward to making other videos. Until we meet again. Bye.